Very good. Welcome back. Uh, Last class, after a few lectures in which we had just been doing mathematics, we started doing physics again. And what we wanted to do was use these probabilistic entropic methods of inference to model quantum mechanics. So we have to make assumptions. The main assumption that we make is that whatever the motion of the particles is, it's going to be continuous. Uh, the implication of the motion being continuous is that you can chop it in little pieces, in short steps. And if you figure out the motion in a short step, then you have a chance to iterate those short steps to produce motion over finite steps, to study finite changes. So what we would like to do today, and this is what makes today's class particularly interesting, is that we're gonna talk about time. Nothing in those curves, those Hamiltonian flows that we had studied in the previous lectures, told us anything about time. We were talking about parameters along the curves, lambdas, and they could be whatever you wanted. What we're going to do now is talk about time, and the interesting feature is that we're going to learn things about time that are not typically considered to be part of what we think of as quantum mechanics. Quantum mechanics uses a basically not a Newtonian notion of time. Quantum mechanics has not added much to our understanding of time. So what we're going to see today is that in this inferential approach to physics, already at the level of quantum mechanics, we learned something. And the basic idea is going to be that time is introduced as a tool that we use a device for keeping track of how these small changes accumulate. Okay, let's take a look at the details of how this comes about. To do that, I need to go to my tablet. And here we are. So last class we had studied the transition probability when your system goes from a system of n particles, goes from a position in the configuration space X to a nearby position X prime. The fact that the step is short is implemented by having a Lagrange multiplier that is large, which with this minus sign here says that any displacement that is big will get killed, has very low probability. The transition probability has the form of which is obtained by using the method of maximum entropy, has the form of a Gaussian distribution. A generic displacement is going to take the form of an expected drift plus a fluctuation. The expected drift is described by, there is the gradient of the drift potential. These two terms come from the two constraints that we imposed on the transition probability, namely one involving the gradient of the drift potential and another one involving external vector potentials to describe electromagnetic effects. So one of these constraints had involved the gradient of this drift potential, and it had a Lagrange multiplier alpha prime. And the other constraint involved the Lagrange multiplier beta. We're going to talk later about this particular combination, but you can already see here that you have some sort of gauge symmetry. If you were to change phi and change A in ways that the changes compensate each other, you still get the same average drift. The fluctuations, of course, the average of a fluctuation is zero. That's the definition of what a fluctuation is, any deviation from the average. And the correlation between these fluctuations is given in this form. So the fluctuations for different particles are and for different coordinates are independent of each other. And what appears there is the Lagrange multiplier that involves short steps that comes from the prior. Very good. So now that we have the transition probability from x to a neighboring point, we would like to iterate this. So what we want to we want to iterate these short steps. So that's the goal. And what we mean by this is that if you start at a definite point in your n particle configuration space, the transition probability will tell you what is the probability of landing at a neighboring point. Once you are given the neighboring point, you iterate again and you go to its neighboring point, and so on and so forth. Eventually, after n steps, you go from the I shouldn't say n steps, I should say I steps. You go from xi minus 1 to xi. Now, the point I want to make here is that the first step, you might have started with a position that was not only well defined, but also known. This is assuming you know x. But by the time you get to the second one, this one has a probability attached to it. It's a definite position, but you're uncertain about it. Same thing with this one, and so on, until this one is unknown, and so is that one. So what this means is that we neither know xi minus 1 nor I at the ith step. So we are led to consider the probability, the joint probability of xi and xi minus 1. Now, what we really want is the probability of the last step. What we want is what is the probability distribution for the particles right now after it's taken so many steps. So the way we're going to handle this is the traditional way of probability distributions, of probability theory, in which we marginalize over the variable we do not want in order to get the variable we want. Please notice that here we're just using probability theory. We're not making any assumptions. Now, nothing prevents us here from using the product rule. And so we're going to write this as the probability of xi given xi minus 1 multiplied here by the probability of xi minus 1. Very good. Nothing here involves any assumptions from physics. This is just the rules of probability theory. If you're uncertain about these two positions, you can always marginalize, and you can always use the product rule. Now we're going to make a physics assumption. What we're going to say, if this is the probability distribution at one instant, this one here is going to be the probability distribution at the next instant, while this term here is precisely the transition probability from x to x prime. So we're going to write this, rewrite this equation by saying this is the probability distribution, we write it as rho, at the time t for the variable x. This guy here is the transition probability of going from x to x prime. We integrate over the x and we obtain the probability distribution of x prime at the time t prime. This is going to be the main dynamical equation. So let me now see what it is that we're doing here when we are introducing a notion of time. The introduction of time, let's do it systematically now. The introduction of time requires three ingredients. One, we have to define the notion of instant. What is an instant? Two, we have to make sure that whatever notion of instant we have introduced, that these notions are ordered. The instants must be ordered. You could try to invent a notion in which a concept or a framework in which these instants are not ordered, but whatever that would be, it would be very difficult to call it time. I mean, if you want to talk about time, you have to have a clear idea of past, present, and future. So if the instants are not properly ordered, you might have something interesting, but it definitely is not what we mean by time. C. You also have to, once you have a notion of instant, you have to introduce a notion of duration. The notion of duration, which is just the length of time between two instants, okay? So let us go back and see what it is that we already started doing here. What we wanted was to iterate short steps. And we realized that soon, not only you are uncertain about the last step, you're also uncertain about the previously immediate step. And this allowed us to write an equation, or rather we made the assumption that if this probability for the previous distribution is given like this, and the probability for the next distribution is written like that. Let me rewrite that equation because it's central. What we're going to be saying is that if this represents the distribution at one instant in time, we can construct the next distribution with this formula. In fact, this is the basic dynamical equation of entropic dynamics. We could even go ahead and say, look, if this defines what we mean by one instant, then that defines what we mean by the next instant. And if we just repeat, put x prime here, x prime, x double prime, integrate over x prime, we get the row of x double prime. So we can iterate this equation, and from one instant, we create the next. We are constructing time according to the information involved in that probability distribution and that probability distribution. So what we have here is an instant is an informational or inferential concept, uh, an instant is a specification of the information that is required to create the next instant. You gotta let that sink in a little bit, okay? If rho is supposed to be some kind of coordinate in some epistemic configuration space, the information contained in the drift potential that is included here plays the role of a momentum. So an instant is a state. It is a state which defines the information that is required to create the next instant. It's sort of amusing, and I'll say this later because it's important, that if the instant is an inferential concept, it's going to end up being an epistemic concept. And yet, as I'm going to argue as we proceed, T may end up being an inferential epistemic concept, but this is the T that's going to show up in the Schrödinger equation. So if you feel nervous about what it is we're doing with this time, this is the T that's going to show up in the Schrödinger equation. And when you build a clock or you calibrate a clock on the basis of the equations of physics, what you're doing is you're inventing a device, a clock, that measures the T that appears in the Schrödinger equation. So you calibrate clocks in such a way as to measure this T. So this T is going to be as physical as it gets. Very much like temperature comes from a beta, a Lagrange multiplier, and therefore it is also an epistemic concept. Temperature is an epistemic concept. It comes from a Lagrange multiplier. And yet, when you calibrate your thermometers, you calibrate them to measure those particular parameters that appear in the Gibbs distributions. So while it is true that temperature is epistemic, you calibrate your devices, your thermometers, to measure temperature. So it's as physical as it gets. Same thing with time, as we shall see. So an instant is an inferential concept. What should I say? Yes, this is interesting. It's when you say the probability for a single particle, when we talk about one particle, the position of the particle is going to be given by 3 coordinates. Now, the particle is a point. It has 3 coordinates. Clearly, you assume that the values of these 3 coordinates are going to be simultaneous. So you have a point particle, right? x1, x2, x3. You're talking about the values of these coordinates at the same time. For n particles, we do something similar. What we have here is a particle is a point. N particles, we have a point in configuration space. And we call this something like x1, x2, x3. This is for particle 1. And then we have x1, x2, x3 for particle 2, and so on. For exactly the same reason, when we talk about a point in configuration space, the idea is that these coordinates and those coordinates are all simultaneous with each other. So this is sort of amusing because while it is true that if you have a point, it is natural to think of the coordinates as being simultaneous, when you have 2 particles that are not at the same spot. The issue of simultaneity is not nearly as obvious. Well, the language we use when we invoke a configuration space assumes a notion of simultaneity. Similarly, when we talk about the probability of a particle having different positions, well, the x1, the x2, the x3, the different positions that appear here, the particle is either here or there, we're going to assume that I do not know the notion of the particle right now. The probability that I'm talking about is the probability of the particle being here or there right now. Same thing for n particles. Whether we talk about distributions for one particle or for n particles, the implication when we write an equations such as this one here is that all of these particles are going to be considered at the same time. So a probability distribution rho xt, let me write it explicitly because it's important. A probability distribution rho tx assumes or defines a notion of simultaneity. So this is what an instant is. An instant is a probability distribution. Very good. Are these instants ordered? Right here, we have this dynamical equation that tells you how you go from one instant to, let's say, the next. But that equation came from having a joint probability distribution and just marginalizing over one of the two variables. Nothing prevents us from having the time reversed equation in which what we have here, let me write it in terms of rho, we have rho tx is equal to the integral dx prime. Here we're going from x prime to x. Actually, I shouldn't say from x prime to x. It's the probability of x given x prime, whether it is earlier or later, who knows. So here we have the same equation, but with primes and non-primes exchanged. So now it seems that if we just look, because this equation takes exactly the same form as this one, it appears that these instants do not have a nicely defined sense of ordering, which is first, which is second, which is earlier, which is later. But actually that is not true, because what you have here is this expression, which is not the same as that one. In fact, the relation between these two probability distributions, probability of x given x prime and probability of x prime given x, is given by Bayes' theorem, which in this case takes the form like that, where this guy here plays the role of a prior. You multiply by a likelihood, you divide by the evidence, and you get the posterior, right? In any case, the crucial point is that while it is true that this equation and its previous version seem to be like very similar, notice that this piece was derived from maximum entropy. And the result is that it gave us a Gaussian distribution. While this guy here, if it is to be consistent with the rules of probability theory, is obtained by taking this Gaussian and multiplying by those factors so that this is not Gaussian. The transition probability is derived from maximum entropy, and it is a Gaussian. The time-reversed transition probability is derived from maximum entropy plus base, and it is not Gaussian. So one of the things that immediately appears here is that there is a natural arrow of time. Very good. The problem of the arrow of time, the traditional problem of the arrow of time, is this puzzle that's been around ever since people discovered the laws of thermodynamics, the fact that entropy increases in thermodynamic problems. And so the question was, how can you explain the irreversibility or the arrow of time, right? The irreversibility of thermodynamics on the basis of laws of nature, like Newton's equations or the Schrödinger equation, that happen to be time reversal invariant. How do you explain the arrow of time coming from underlying laws that are time reversal invariant? The puzzle. So this is the puzzle. How do we explain the arrow of time from laws of physics that are time reversal invariant? So here's the answer. ED does not assume underlying laws of physics. So whether they are time reversal invariant or not, ED does not assume any of that, and you naturally get an arrow of time. So the challenge here, the challenge for ED is very clear. How do you explain on the basis of a theory that includes a natural arrow of time the fact that the Schrödinger equation ends up being time reversal invariance? So the challenge is to explain laws that are reversible, time reversal invariant, when the basic notion of time is directed, is not invariant. How do you explain that? Well, we're going to see. That's our goal, right? This is what we have to explain. But in any case, what you can start seeing here is that the big puzzle, the historical puzzle of the arrow of time, has been solved here in a very, very peculiar way, not by assuming that you have laws of physics that are doing something peculiar, but rather by assuming that you have no laws of physics. In fact, Entropic time, the t that we're talking about here, only goes to the future because the particular way in which we are explaining or deriving our model is one in which we maximize an entropy. If we maximize an entropy starting from x, we go to x prime. If we maximize an entropy starting from x prime, we do not go to x. If we start from x prime and we maximize the entropy for the transition probability, we do not go to x, we go to x double prime. Entropic time only flows forward. Very good. There is an arrow of time. Instants are ordered. And now what I would like to address is the last issue here, the notion of defining the duration. What is the length of time that takes you from t to the next step? In fact, we do not know what it is that this t prime is. How much later should this t prime be relative to that one? When we look at, so C, how we define duration. So the idea here is simple. Duration is defined so that motion looks simple. It's as deep as that. In classical mechanics, let's see how it's done in classical mechanics. In classical mechanics, the prototype of a clock is a free particle. You might think that a clock is something that looks like a pendulum or something like that, but no, that's too complicated. No, the prototype of the ultimate clock that defines the theory is really a free particle. And the way we define time is that the particle that's free will move in a straight line, right? And so we define time so that the particle moves equal distances in equal times. And so because this, if you just make sure that this is the same distance, we're going to say that the same distances, this leads to same delta t's. In other words, we define time so that a free particle moves in a straight line at constant speeds. So in classical mechanics, the clock is a free particle. Duration is defined so that the speed is constant. So that's what we do in classical mechanics. In quantum mechanics, in entropic dynamics, we do exactly the same thing. We have to be very careful because when you have something like an equation of motion that looks like this, where the actual dynamics really is controlled by this transition probability, that's here, it is not clear at all where you have a straight line, right? Where do you have a free particle? Well, both in quantum mechanics and in classical mechanics, the idea is that for sufficiently small intervals of time, the particles are going to be essentially free. Basically, no forces have had time to act. So what we really want, when we want to define a notion of time, define the measure of time, define duration, is we want to make sure that these particles have well-defined velocities. That's the point. Now, we look at the average displacements here, the drifts, and we want this to be an average, a well-defined velocity, to lead to a well-defined velocity. Very good. So let us proceed by saying, if you have an equation like this, where would the actual dynamics be described? It's it here. And if we want to have something that lets me go from t to t prime, I have to make sure that this quantity here involves the t prime. If that quantity has a t prime, and it takes you from t to t plus delta t, the delta t has to be contained in the Lagrange multipliers. So now it is that we define what the Lagrange multipliers are. Remember how this worked. We introduced constraints, expected value of this, that equals kappa. But I never told you what the kappa was. I did mention at the time, it's going to be much easier to, instead of telling you what the kappa is, to tell you what the Lagrange multipliers are. So this is where we do it. We're going to define the Lagrange multipliers in such a way that this guy here contains a delta t, so that when you divide by delta t, you have a well-defined notion of velocity. Let's do that. So in classical mechanics, duration is defined so that the speed is constant. Why? Because that makes the motion the simplest possible. In entropic dynamics, we define duration so as to reflect, I'm being a little bit more sophisticated here, instead of just telling free particle moving in straight lines, reflect the translation symmetries of space and time. And what that means is we're going to define those Lagrange multipliers. Let's go back to the beginning. This is when I'm telling you what the alphas are and how they're connected to time. You need a delta t here in order to have well-defined velocities. So we're going to say that whatever this is, there is a delta t. This guarantees that there may be a constant here, a constant that depends on n. This guarantees that there is going to be a well-defined velocity. But let's look at it a little bit more at what I have done here. Could this object here depend on positions, or maybe even on t? Well, not really. What we want here is something that reflects the translation symmetries of space and time. So I'm defining these Lagrange multipliers themselves to be independent of space, independent of time. So what this tells you, the fact that I'm setting this to be a constant, independent of x and of t. So what I'm making sure is that time flows at exactly the same rate everywhere. The delta t over here is going to be the same as the delta t over there, right? It flows everywhere at the same speed. It's the same delta t. And also every when. Whether the delta t tells you about the transition from Monday to Tuesday or Tuesday to Wednesday, what really matters is the difference, t prime minus delta t, and not the absolute value or the location of the t. So this is what Newton would refer to as time flows equably everywhere and every when. We're using the same ideas because our goal here is to reproduce non-relativistic quantum mechanics, and so we're trying to reproduce the symmetries of Newtonian time. So this is what achieves it. But let me rewrite this in a better way. This is supposed to be proportional to t, and the constant that appears here is supposed to include an index that tells you that different particles could conceivably have different alpha n's. So I'm going to rewrite this constant. It's a particle-dependent constant. I'm going to write it as m. And this is just constants. And then I'm going to make sure, there is a reason why I wrote it like m, right? Because at some point when we get to the Schrödinger equation, we're going to realize that t that appears there is the t in the Schrödinger equation. And this m that appears here, which is just associated to the alpha n, that this m is going to be the mass of the particle. Furthermore, if we want this guy to have the units of mass and that guy to have the units of time, we need to have a constant here that sort of adjusts the units. And we're going to introduce that constant, and that constant is called, we're going to call it h bar. We have no idea how this guy is connected to Planck's constant, but once we get to the Schrödinger equation, that's what this guy is going to be. So here there are essentially no assumptions. Had entropic dynamics been invented in 1923 before Heisenberg and Schrödinger came up with the real equations for quantum mechanics, it might very well be the case that we would have called this Cn and proceeded all the way to the end. As it is, eventually we're going to get to the Schrödinger equation, and we're going to realize that the Schrödinger equation is telling us you calibrate clocks in such a way that they measure this funny parameter t, and you calibrate your balances, devices to measure weight, in such a way that what you're actually measuring, or mass of course, are these m's. So this is going to end up being the quantity that we call mass eventually. But at this point, we do not know that. So that's how we define duration. But I have just defined the ratio. If I want to actually figure out the full thing, we need not just the ratio, but we need also to have the alpha n's, that are the Lagrange multipliers that enforce short steps. So we need to either define alpha prime or alpha n. So to finish the construction of time, we need to define alpha n or alpha prime. The choice of alpha prime or alpha n is not unique. This is actually very interesting. I'll mention a little bit more in a little while, but what alpha prime do we pick? It is interesting that the choice of alpha prime is not unique, but this does not affect our derivation of the Schrödinger equation. Now this is interesting, and we're going to talk. I'll talk a little bit more about it later. But what we're trying to do is derive the Schrödinger equation that's supposed to describe the behavior of electrons and atoms and things like that, right? But one of the things that is emerging from this approach is that whatever the Schrödinger equation is an equation for the evolution of probabilities. And this evolution of probabilities would be somehow analogous to the evolution of macro states in thermodynamics. So the Schrödinger equation is sort of like a macroscopic limit, while when we're trying to figure out these transitions from x to x prime and all of that, we're talking about the micro states at the micro level. So let's call it the quantum level and the subquantum level. The choice of alpha prime will turn out to be not unique, but you can make different choices of alpha prime, and this does not affect the dynamics at the quantum level. It does affect the dynamics at the subquantum level. I'll come back to this later. The choice of alpha prime is not unique. We're going to choose, we shall choose an alpha prime that is useful or is convenient. We shall choose, and it will become clear now in a second why it is that this is convenient, is something in which the alpha prime is inversely proportional to delta t. There is going to be a constant here. You see, alpha prime does not depend on n. The alpha prime was the Lagrange multiplier that came from the drift potential. It was a single constraint on the whole configuration space. So no n here, so this is just going to be a constant, and we're going to choose the constant conveniently and introduce yet another constant here to be determined later. It's sort of interesting that this constant drops out from the Schrödinger equation. So this is one of the pieces of evidence that we have that the alpha prime, you can play games with the alpha prime, and it makes no difference in the end. Which, if you have that alpha prime and you have the ratio of alpha prime alpha n, then the alpha n is mn eta delta t cubed. Now you see, remember how the alpha n worked? It had to be large in order to ensure short steps. Yes, look, as delta t goes to 0, this is large. So this ensures really short steps as you take the limit as delta t goes to 0. In the continuum limit, this gives you short steps. Very good. So what do we have here? What we have here is a probability distribution, a transition probability distribution, which is of this form, minus 1 over 2 eta delta t. Before we do this, we're going to use a notation that is more convenient because our indices were starting to get a little bit out of control. So we're going to use a notation that's convenient for configuration space. We're going to use indices, capital indices, which are going to reflect both the particle and the coordinate. So our index here is going to be AN, a composite index, and of course we're going to need another composite index here. It's going to be B N prime. And what we're going to do is we're going to let a delta function, for example, here will be something like delta n prime delta a b. And so we're going to define our mass tensor. The mass tensor is going to be MAB, and it is a convenient way to write in our probability distributions to write all the masses that appear there. This is going to be n prime delta AB. The inverse, so we can actually write all this also as mn delta AB, knowing that the capital A includes an n. So this is a diagonal tensor that includes m1, m1, m1 for the first particle, m2, m2, m2 for the second one, and so on. And the inverse, we're going to write it as like that. Very good. Then the transition probability can be written in somewhat simpler form. It's going to be -1 over 2 eta delta t, and then there is this tensor that takes care of all the scalar products, delta x a over delta t minus va, and then delta x b delta t minus v, where va is the expected value of delta xa divided by delta t, and this is equal to the inverse mass tensor, the phi minus a b. Previously, where we have this, maybe let's keep going. Here we have a lowercase phi, and here we have an uppercase phi. This uppercase phi is going to be equal to the drift potential that we had before. We're also going to call it the drift potential, not that, but multiply by h, just because. Why do we want to do that? Well, we want to do that because this guy is going to be called the phase, and it's the object that's going to end up showing up in the in the wave functions. There is a reason why we want to write it like this, with absorbing the h bar that was somehow floating around in those alphas. We want to write it like this. It's because this form for the velocity written in terms of 1 over m gradient of phi, that's the typical expression that you get in the Hamilton-Jacobi approach to classical mechanics. So what we want to do here is we want to write or introduce our definitions in such a way that they start looking more and more like the notation that's normally used in physics. So this is standard notation. The a bar that we have here, the vector potential, was a quantity defined in three-dimensional space. Now we are defining it in configuration space. Well, the idea here is that when we write something like that at the point x, this quantity by definition is nothing else but Lagrange multipliers, constants that make things look easy here. And then here we have the coordinate A at of the particle AN. So this is just a trivial change of notation. Very good. So here we have the transition probabilities. You can see that they're still Gaussian. I have written here, remember I have here alpha n is delta t cubed. The alpha n appears here in front, and we have delta t, delta t, delta t. That's why this definition was so useful. What we have here is a velocity that has an average v, which is defined here, the average velocity, and there are fluctuations, and the fluctuations go to 0 as delta t goes to 0. So let me write what the fluctuations are, so that delta x a is equal to a velocity. We defined time so that this was true, okay? Plus a fluctuation in configuration space. And where the fluctuations, as always, have zero average, and in this case, the fluctuations of position go to 0 as delta t goes to 0. That's the expression. We can also rewrite it like this. Or I'm going to rewrite the fluctuations here. I'll rewrite them as delta x minus v delta t. So I'm going to write this as so what I'm doing here is I'm writing the fluctuation as delta x minus v delta t, and I'm dividing everything by delta t. So that's one, that's the other. And so what I get here on this side is eta MAB delta t. So the fluctuations in velocity go to 0 as delta t goes to 0. So what this means is that the particle velocity is the limit as delta x divided by delta t as delta t goes to 0. This is going to be equal to VA. These particles have nicely defined velocities. The trajectory is smooth, it's continuous, but not only continuous, the trajectory is smooth. So these trajectories are continuous and differentiable. What else? One last remark. We have defined time so that the motion looks simple. Namely, we have defined time so that the particles have well-defined average velocities. But with this definition of time, we achieve even more. The particles have continuous and differentiable trajectories. Remark. If we had chosen alpha prime equals constant, Instead of alpha prime, here we have our alpha prime be 1 over delta t. If we had defined our alpha prime to be a constant, and in this case we could just do something like this, then our transition probabilities would also look very nice and Gaussian. They would look very similar, except that instead of being a Gaussian in the velocities with a 1 over delta t in front, it would be a Gaussian in the displacements with 1 over delta t in front. So what this means is immediately that the fluctuations would be, it's a matter of computing it. I'll just give you the answer. It would be something similar like that. As delta t goes to 0, the fluctuations are go to 0, but the fluctuations are of the order of delta t to the 1/2. You see here what we have is that the square of fluctuations is something that goes like delta t. The fluctuations themselves are going like delta t to the 1/2. So if you try to figure out what the velocity is by dividing by delta t, what you have here is an object that goes like 1 over delta t to the 1/2, and it explodes, right? As delta t goes to 0, this explodes. Such a velocity with this choice of the alpha prime, the trajectories are still continuous. Look, the fluctuations here go to 0, the velocity of the particles is well defined, the average velocity is well defined. The particles would follow trajectories that are still continuous, but the velocity is not defined. They are not differentiable. This is a Brownian motion. Trajectories are continuous, but not differentiable. The notion of the tangent to the trajectory is not defined. So these are extremely irregular motions. Now, what I would like to emphasize is that the continuous trajectories or the Brownian trajectories are both equally good models for what's going on at the subquantum level. At the quantum level, both lead to the Schrödinger equation. My own personal belief at this point is that we cannot tell which is the true one. Future theories, future experiments may actually give us hints as to what is the correct way or which is the one that better fits future experiments. But to the extent that both lead to the same Schrödinger equation, we can safely conclude that the experiments that were used to do in quantum mechanics will not find any difference between these two subquantum motions. To study the subquantum motions, it may actually be more legitimate to try to do a relativistic quantum mechanics, but that's for some other course. See you in a little while.